All right, so now in 6.2, we're going to solve more systems of differential equations, but now we're going to get complex eigenvalues, and we're going to see what happens when you have a complex eigenvalue. So we're going to solve this system. It has an initial value. So we need the coefficient matrix. We need to find the, let me change my size here. We'll need to find the eigenvalue, so we're going to find the determinant of A minus lambda I, which just, of course, subtracts lambda from the main diagonal. All right, so I multiply 3 minus lambda times negative 3 minus lambda, and we're going to subtract negative 10, negative 5 times 2. It's going to be plus 10. So I need to multiply the binomials together. So that looks like I get negative 9, negative 3 lambda, plus 3 lambda, plus lambda squared, and then plus 10. Rewrite this, lambda squared. The minus 3 lambda plus 3 lambda is going to cancel out. Negative 9 plus 10 is plus 1. So you see this is not a factorable polynomial, but we can use our square root property. I can say subtract 1 from both sides, plus or minus the square root of both sides. Square root of negative 1 is I. So here are my two imaginary or complex eigenvalues. When you get complex eigenvalues, they always come in conjugate pairs, just like when you, if you're solving a polynomial equation and you get complex solutions, they always come in plus or minus conjugate pairs. So let's find the eigenvectors. So let's solve. Let's do this first. Let's say for lambda equals I, we'll do plus I first. We're going to solve A minus I times I, sorry about that, there's two different I's there, times x equals 0. This will be our first eigenvector, so we'll call that x1. So we need to subtract imaginary I from the main diagonal. So it's going to be 3 minus I, negative 5, 2, negative 3 minus I. And we augment this with 0, the 0 vector. Now we got to solve this system. Now, you may not have ever solved a system with complex numbers in it, but it's not too bad. So first I want to make this entry a 1. So I'm going to first turn it into a real number instead of an imaginary number. So I'm going to multiply this, let me change colors here. I want to multiply this row by the complex conjugate, 3 plus I. That's going to make this entry in my new matrix a real number. So let's multiply these. You have to fold it out, just like we did up here, right? We've got to fold this out. So that's 9. And then I've got negative 3i plus 3i, that's going to cancel out. And then I have minus I squared. And then I have 2 times 3 plus I. And the second row is going to stay the same. So what is I squared? I squared, well, since I is the square root of negative 1, then I squared has to be negative 1. So this is negative 1. So this is 9 plus 1, which is 10. Let's multiply this row by -1. If you notice, the second row and the first row are multiples of each other, right? So this first row is actually 2 times the second row. So when that happens, you know you're going to get a system that's going to have free variables, and that's got to happen in all these where you're solving for the eigenvector. You have to get a free variable to even get a non-zero eigenvector. So I'm going to multiply this by -2 and add it to the first row, and then I'm going to switch the rows, and that'll give me 5, 3 plus I in the top row, and zeros in the second row. And again, augmented with 0. So now I just need to, we could divide by 5. We want to reduce it all the way. So I get 1 and then 3/5 plus 1/5 I. And now I'm ready to get my eigenvector. So this one has a leading 1. This one is free. So I'm going to say component x1 is the negative of 3/5 plus 1/5 I times x2, and x2 is free. Right, these are the coefficients of x1 and x2. x1 and x2 are going to be the components of our eigenvector. So we get to pick x2. Let's let it be 5. Actually, let's let it be -5. And then that'll cancel out this negative here when we plug it in for x2. So that's going to make our eigenvector, our first eigenvector is going to be -5 for x2, and then in the top for x1, negatives are going to cancel out. I'm going to multiply by 5. That's going to cancel out these 5s. I'm going to be left with 3 plus I. So there is my first eigenvector. So let's find the second eigenvector. It's going to be very similar, right? We're going to say for lambda equals -I. Now we're going to solve a plus I times I. Again, sorry about the double I's there. And we're going to solve for vector x2, our second eigenvector. So instead of subtracting I, we're going to subtract -I, which is going to be the same as adding plus I. Go back to my original. We're going to do the same process again, right? So I need to multiply by the conjugate here. Let's pick 3 minus I. Now you might find an easier way, a quicker way to do this, but I'm just going to show you how to use this conjugate. So it's 9. We have 3i, -3i, that's going to cancel. And then I have a -I squared, which is, I squared is a -1, so the negative of it's going to be +1. So this is going to be 10 again, right? It should be the same because these are the same two things we multiplied here, right? All right, then I have 2 times 3 minus I. On the bottom, let's multiply by -1. And again, you can see that the first row is 2 times the second row. So this is going to reduce in a similar way that the last one did. Going to reduce it to We're going to have zeros in the bottom row. Going to move the 5 and 3 minus I to the top row. And then I'm going to divide by 5. And you could write it like that. You know, I wrote it a different way last time, but you can write it like this. It's just fun. It's going to get the same thing. So x1 is the negative of 3 minus I over 5 times x2. And let's let x2 be something that's going to help us out. Let's let it be negative 5. So our second eigenvector, negative 5 in the bottom, we're going to get 3 minus I as the first component. And if you remember, what was the first eigenvector? First eigenvector was 3 plus I and negative 5. So that's interesting. These two, you could say these two vectors are conjugates, right? We took the complex number and just take the conjugate of that and you get the other eigenvector. Is this true all the time? It actually is, right? It's actually true if your eigenvector, let's say if your eigenvalues are complex conjugate pairs, their eigenvectors can be complex conjugate pairs. They will be complex conjugate pairs. You might get different forms, but you know, we could have picked a different x2 here and it would look different. But because I picked the same one, I got exactly the complex conjugate. So in actuality, we didn't need to necessarily do all this work, you know, from here down. Knowing what we know now, we're not going to have to do all this because we're going to know what the other eigenvector is. And in fact, I'm going to show you that really all we need is this one eigenvector. We don't even need the other one at all. So I'm going to show you that next. So now we got to write our solution. So let's, let's write the solution the way we would normally write it. Say y is C1 e to the IT 3 plus I negative 5, and then C2 e to the negative IT, and then 3 minus I negative 5. So if we just look at this part of our solution, so we'll call this y equals e to the IT times the vector 3 plus I negative 5. Now remember, when we were doing second order equations, we used Euler's formula to get rid of this imaginary I. So let's look at that again. So what is Euler's formula? Euler says e to the I theta is cosine theta plus I sine theta. So here we're just going to replace theta with t. I'm going to change e to the it into cosine t plus I sine t times the same vector, 3 plus I and negative 5. And now I'm going to actually multiply cosine t plus I sine t inside the vector. I'm going to have to FOIL on the first component and just distribute on the second one. So we're going to get a new vector. So we get cosine t times 3, so it'd be 3 cosine t times I, and then I sine t times 3. Then last we get I sine t times I, so that's going to be plus I squared sine t. And then for the second component, it's just going to be -5 distributed inside cosine t plus I sine t. So we get -5 cosine t minus 5I sine t. So this I squared we can replace with -1, right? Because I is equal to the square root of -1. So if we square I, we're just going to get -1. And we're going to do something clever here. We're going to separate or decompose this vector into two separate vectors. I'm going to take everything that has real components and put it in the first vector. Everything that has imaginary components, I'm going to put it in the second vector. So in the first vector, I'm just going to look for the ones that are real, the ones that do not have the imaginary I. So that's going to be 3 cosine t and then minus sine t. So we change that I squared to -1. And then the denominator, or sorry, not the denominator, the second component, we have -5 cosine t. And then the other side, the other vector, we're going to include everything that's got imaginary I inside. So we'll have I cosine t plus 3I sine t. First component, and then second component is going to be -5I sine t. Now in the second vector, since each term here has got an I, I'm going to factor out that I. So I'm going to say first vector plus I times the second vector. The second vector is going to be cosine t plus 3 sine t, and then -5 sine t in the second component. So now, if you remember from, again, when we were doing second order equations, we said if function u plus I times function v was a solution, then u and v are also solutions. And what's important about that is we drop the I. So this vector that's u plus I v, if that's a solution, then we can consider u by itself a solution, and we can consider v by itself a solution without the I. And the question is, well, does that also work with the vectors? Because here I have vector u plus I times vector v. And the answer is yes. Color didn't change there. If I just change these to vectors, the same thing holds for these vectors, which is nice. I'm not going to prove it here, but you can look at that and see if you agree. So that means that this vector is a solution, and so is this one. And you only need, in this case, we need 2 linearly independent solutions. These guys are going to be linearly independent So you can show that. I'm not going to show it here, but these guys are automatically linearly independent. You can show it with the Wronskian, right? If you compute the Wronskian, you can see that these vectors are independent. So that means I can write my solution with just these two. So I can say y is C1 times this first vector, 3 cosine t minus sine t minus 5 cosine t, first vector, plus C2 times the second vector, cosine t plus 3 sine t minus 5 sine t, the second component. And that is our new general solution. And notice that there's no I. We got rid of the I. And I only used this first eigenvector eigenvalue combination here, and I was able to split it into two separate solutions that were independent from each other, and that gives me an easy way to get rid of those imaginary numbers and an easy way to get my solutions. All right, so we're actually not done here because this is an initial value problem. So let's go back to the original problem. What's the initial value? We're given that y of 0 is 3, negative 1. And this 0 is t, right? We're going to let t be equal to 0, and then we're going to set it equal to 3, negative 1. So we're going to solve for these constants here. So I'm just going to figure out what is y of 0. So I'm going to plug in t equals 0. So I got 3 times cosine 0. Cosine of 0 is 1. So that's 3. Sine of 0 is 0. So I just have 3 in the first component. And then on the bottom, cosine of 0 is 1. So times negative 5. So second component is negative 5. Do the same thing for C2. Second vector, cosine of 0 is 1, plus 3 times sine of 0 is 0. And second component, again, sine of 0 is 0, so we get 0 there. And we set this equal to 3, negative 1. We're going to solve for the two constants. So I'm going to put this in a matrix. And let's see here. Let's divide the second row by negative 5 and put it into the first row. All right. And let's, I'll just write this one down the second row. And now let's take the first row times negative 3 and add it to the second row. So I've got 3 minus 3 is 0. 1 minus 0 is 1. And I've got 3 minus 3/5. So 3 minus 3/5. 3 is 15/5 minus 3. So it's going to be 12/5. So there's C1 and C2. So I can write the particular solution 1/5 times 3 cosine t minus sine t over minus 5 cosine t. I keep saying over like it's fractions. It's the second component. And then plus 12/5 times the second solution, cosine t, I think that's minus, nope, plus 3 sine t, minus 5 sine t in the second component. That's our solution. We can actually simplify this. We could write this as one vector if we wanted. So let's do that. Let's multiply these scalars inside the vectors. So first vector will have 3/5 cosine t minus 1/5 sine t. And the second component is just going to be negative cosine t. The 5's will cancel. And second vector, first component, 12/5 cosine t plus 36/5 sine t. Second component, negative 12 sine t. The 5's cancel out. So now we can add these together. And let's see, 3/5 plus 12/5, that's 15/5, which is going to leave me with 3 cosine t. And I've got 36/5 minus 1/5, that's 35/5, that's going to be plus 7 sine t. And then the second component, negative cosine t minus 12 sine t. So that is a lot simpler solution than this guy. So that's probably preferred here. So let's do another example. This is not an initial value problem, but we're going to go through the same steps, and we just won't do the last part at the end. We'll just get a general solution. But I need the coefficient matrix. What is A? -3, -2, 5, -1. Right, so this system's x prime equals -3x minus 2y. Y prime equals 5x minus y. So A is -3, -2, 5, -1. So we need to find the eigenvalues of A. So we're going to find the determinant of A minus lambda I, and you just end up subtracting lambda from the main diagonal. So we need the determinant of that matrix. So we're going to multiply -3 minus lambda and -1 minus lambda, and then plus 10. Right, we're going to subtract 5 times -2, so it'll be plus 10. So that's going to be 3 plus 3 lambda plus lambda squared plus 10. And I'll just rewrite this. Lambda squared plus 4 lambda plus 13. We can see here that's not going to factor, right? So we could use quadratic formula, but this one looks easy enough that we could just complete the square, right? So let's see if we can complete the square. I'm going to move the 13 to the left. And b is 4, so b divided by 2 would be 2. And then squared is 4, so I need to add 4 to both sides. So this is lambda plus 2 squared. That's since this is a perfect square. And this is 4 minus 13, that's -9. So here when I take the square root of both sides, I get plus or minus 3i, because that's the square root of -9. So there's my complex part. And then I subtract 2 from both sides. I get lambda is -2 plus or minus 3i. So I have these two complex eigenvalues. But remember, we just need one, right? If we just have one eigenvalue and one eigenvector, we can create the two solutions that we need. So let's say for lambda equals -2 plus 3i, we need to solve this equation. We need to solve a minus -2 plus 3i times I times the eigenvector x set to 0. We're going to solve for this x. That's our eigenvector. So I'm just going to distribute this. So we get plus 2 minus 3i times I times x equals 0. So we're going to multiply I times 2 minus 3i and add to a. So it's going to be like taking the main diagonal of a and adding 2 plus 3i. So our main diagonal is -3. So I'm going to say plus 2 minus 3i. And then the other main diagonal is -1 plus 2 minus 3i. I think this was 5 and -2. My pen turned into an eraser. I don't know. The eraser works, but the pen still looks like an eraser. I don't know. Messed up. So let's simplify this just a little. So -3 plus 2 is -1. -1 plus 2 would be +1. Still augmented with 0. So I want to multiply this row, this first row, by the complex conjugate. So I want to multiply this row by 1 plus 3i here. And for that first component of the first row, we're going to have to full it out. So -1 times 1 is 1. And then I've got plus 3i minus 3i. Those are going to cancel out. And 3i times -3i, that's going to be -9i squared, but the I squared is -1. That's going to cancel out with this negative sign, so it's going to be +9. And then I've got -2 times -1 plus 3i. I didn't change the second row. So simplify again. That should be not equals, but a row reduction. This is 10. If I factor out -1 from this, that'll leave me with 2 times 1 minus 3i. Just so I can see that these are multiples, right? So it's going to work out kind of like the last one did, pretty similar. And if I multiply this by -2 and add it to the first row, and then move the second row to the first row, I'm going to get this. So I get 5, 1 minus 3i, 0, and then a row of zeros in the second row. And then let's divide by 5. You might can see that you don't necessarily have to do this step completely all the way out, but I think it might help to see it. Leading 1 in the first column, no leading 1 in the second column, so that means this one's free. So I can say component x1 is the negative of 1 minus 3i divided by 5 times x2. Component x2 is free. So let's set it equal to -5 again, kind of like the last problem. So my eigenvector x is going to be 1 minus 3i and negative 5. And there's no need to find the second eigenvector. This is all we need. So just remember that this is getting plugged in. This negative 5 is getting plugged in for x2. So the negatives cancel out, the 5 cancels out. So I'm just left with 1 minus 3i in the first component. So now we're going to write down one of the solutions that we could get from this. We could say y would be equal to e to the eigenvalue. What was the eigenvalue? Negative 2 plus 3i. So e to the negative 2 plus 3i times t times the eigenvalue, or sorry, the eigenvector. So notice this isn't exactly in the form that we need for Euler's. Right? Euler's is e to the I theta, it's cosine theta plus I sine theta. So we need to change this a little bit. So I'm going to say this is equal to e to the negative 2t times e to the 3i times t, and then times this vector. So just think about distributing the t in the exponent and then splitting that sum into two different e's, right? So if I multiply these back, I'm going to add the exponents, right? And I'll get back to this if I factor out the t. So now I can use Euler's. So this is e to the negative 2t times, I'm going to use Euler's formula just here, just on this guy. So my theta is now 3t. That's my angle, I times 3t. So it's going to be cosine 3t plus I sine 3t, and then times the vector. And now we need to multiply this cosine 3t plus I sine 3t inside here. I'm going to leave this e out front. I don't really care about that guy. I just need to keep it there out front. So I have to full it for the first component. So I get cosine 3t minus 3i cosine 3t plus I sine 3t. And then I get minus 3i squared. That's going to be plus 3 sine 3t, because I squared is negative 1. And then negative 5 times cosine 3t, negative 5 times I sine 3t. So now I want to identify the real stuff, identify the imaginary stuff. I'm going to split them up into two separate vectors, and I'm going to factor out I. So here I'll have e to the negative 2t times the real stuff, cosine 3t plus 3 sine 3t, and then the bottom in the second component, negative 5 cosine 3t plus I, and don't forget the e to the negative 2t, right? And then all the imaginary stuff. So let me put this sine first. So we'll say sine 3t minus 3 cosine 3t. And then negative 5 sine 3t in the second component. So now I can treat this guy and this guy, the first and second vectors, as separate solutions without I. So now I can write my final solution that has no imaginary parts to it. So I'll say C1 e to the negative 2t. You can multiply that inside if you wish. Cosine 3t plus 3 sine 3t. Negative 5 cosine 3t in the second component. Plus C2 e to the negative 2t. Sine 3t minus 3 cosine 3t. And the second component's minus 5 sine 3t. And that is our big general solution of the system. We didn't have initial value, so we're just going to stop here.